It was in 1819 when Hans Ørsted discovered that if you have a wire and there is electrical current flowing through it, that it causes compass needles to line up around it. He found an electric field that looks like this. Now, that electric field actually has a direction to it, to what we call its curl. And to find that direction, we have created what's called a right-hand rule. You know which hand is your right hand? All right, here's the deal. If you have a current flowing, you point your thumb in the direction of the current and your fingers curl in the direction of the magnetic field. So in this case, if current is flowing this way, the field would be going around like this. If current was flowing downward, then the field would be flowing around like that. If the current was going this way, then it's a little awkward to do, but it would be flowing around like that. If current was flowing back towards me through this, then it would be then the magnetic field would be curling this way. So that's the right-hand rule for a long, straight, current-carrying wire. And through a very long, tedious process of measuring how much the compass needles would deflect based on how far away they are, André-Marie Ampère discovered this relationship, that the magnetic field is proportional to the current and inversely proportional to the radius, multiplied by this constant, which is mu naught over 2 pi. Mu naught has nothing to do with coefficient of friction, okay? This is the permeability of free space. It's a constant of the universe that tells us essentially how well magnetic fields can spread through a vacuum. So this relationship, mu naught is 4 pi times 10 to the minus 7 Tesla meters per amp. And that is a pretty small number. It tells us that the vacuum doesn't stop magnetic fields that well. So if current-carrying wires create magnetic fields, if we turn on a current through a wire, we can get it to jump. If we turn the magnet around, let's try that again. Look, another jump, but this time in the other direction. Pretty cool, huh? Now let's do something particularly interesting. Let's swap this around and put it on AC current, so the current is going to flip direction 60 times per second. Watch what happens here. Pretty cool, huh? So, I have a question for you. If you had two parallel wires that were carrying current in the same direction, would they attract or would they repel? So, let's say we have one going this way and then another one next to it going this way. The right-hand rule tells us that the one closer to the camera here has a magnetic field that in between the two is pointing up in the air. And the one farther from the camera has a magnetic field in between the two that is pointing downward. And so we have up and down, those are opposite fields. What do opposite fields do? They attract. The two wires will jump together. So now that we know that a straight wire is going to create a magnetic field, what happens if we take that wire and we make a loop out of it? Well, that is a little hard to picture. I mean, just doing like this, you can actually get an idea of a magnetic field and say, oh, it's doing either this or this. Those look a lot like the magnetic field lines of a bar magnet. But what we discovered was that it's actually easier to just come up with a new right-hand rule. If you have a loop of wire or many loops of wire, then we can do this. Curl your fingers in the direction of current, and your thumb will point in the direction of the north pole of the magnet. So if you have a loop here, like this, my fingers curl like that, the North Pole would be upward, whereas if the current were flowing this way, the North Pole would be downward. So you can take one ring or multiple rings, what we call a solenoid, and we can create a magnetic field that way. Now, the magnetic field strength inside a solenoid, which a solenoid is an electromagnet, right? So the magnetic field strength in there is this. It's mu naught times the current times the number of loops you have divided by its length. So number per length is usually easier to use. It's like the loop density rather than the raw number of either one, because you can make a short electromagnet or a long electromagnet, but if it's got the same number of loops per length, then those are going to be the same strength. But follow that right-hand rule and you'll know which way is the North Pole, which way is the South Pole. We can then switch North Poles and South Poles in order to cancel magnetic fields out or reinforce them. So for example, the doors we have in the hallways that automatically close with the fire alarm, those are spring-loaded and they want to close. They're being held by a permanent magnet and an electromagnet. When the power goes out, the electromagnet fails and the permanent magnet isn't strong enough by itself to hold the door, so that pops free and the door closes. The reason you have the permanent magnet there at all is so that you're not using extra electricity that you don't have to run the electromagnet. The electromagnet only does that last little bit of extra help. We can, of course, use electromagnets to pick up things like junk cars and move them around and then let them go easily. It's nice to have magnets that you can simply turn on and turn off. So let's go back to our wire jumping in our magnetic field. That wire, what direction is the force going to be and how do we know? It won't surprise you to learn that we have a third right-hand rule. I call this one the flat hand rule because unlike the previous two, your fingers aren't going to curl. Your right hand is stuck in this geometry, okay? You're not allowed to bend your fingers, not allowed to bend your thumb. No doing this. All right, no chicken winging and doing that, all right? So you have many magnetic field lines, and you have many fingers probably, and so your fingers represent the magnetic field lines. Typically, we're talking about one wire or one particle or a stream of particles, and you have one thumb, probably, and so you point your thumb in the direction of positive current. Your palm does the pushing. Your palm tells you the direction of the force. Some people teach the rule like this, where you say current, magnetic field, and force. I like it this way more. Magnetic field, current, and your push is your force. Just keep in mind that your thumb always has to point in the direction of positive current. So we can go back to that magnet and say, if we know which direction the electricity was flowing, I can figure out which side of this magnet is a north pole or a south pole. If my current is flowing this way and it jumps up in the air, then the current going this way, that means my thumb has to go this way. It jumped up in the air, that means my palm has to go up in the air. That means the magnetic field is going this way. That's the north pole, that's the south pole. And by the way, I'm gesturing around in free space here with 3D. We have currents this way and fields that way and forces that way. Trying to keep track of things in 3D can be tough, and it can be especially hard if you have a piece of paper and you have it flat on your desk, but you're looking at the board where I've got something written up here. Well, when I say up, from my perspective, up is towards the top of the board, but from your perspective, up is literally up out of the page. So we need to be careful about the words we use when describing directions when we're talking about magnetism. And so to that end, we're never going to use up or down unless they're accompanied by other words, and I prefer not to use them at all. So left is left, right is right. Into the page, out of the page, top of the page, bottom of the page. That way you can take your paper and you can say, oh, okay, when I said top of the page, which is that way, and you said top of the page, which is this way, when you take your paper and you hold it up, we agree on the answer. So into the page, out of the page, top of the page, bottom of the page, left and right. In order to represent these things in 3D, because they can be hard to draw, anything that is coming out of the page is represented by a dot, sometimes with a circle around it, and anything that is going into the page is represented by an X. There's no good reason for that, but one way that might be able to help you remember that, if an arrow was moving away from you, you would see the X of the fletching of the feathers, and so X is away from you, that's into the page. Whereas if an arrow were coming at you, you may want to rethink your life choices that brought you to this point, but if an arrow was coming at you, you would see a point, you'd see a dot. And so the dots are out of the page and the X's are into the page. And so those are our three right-hand rules. For a long straight wire, your thumb is current and your fingers are magnetic field. For loops of wire, it's the other way around. Your fingers are current and your thumb is magnetic field. And for an external magnetic field, putting a force on a wire or a current, you have your magnetic field are your fingers, your thumb is the current, and your palm is the force. One final note, because the force on a charged particle is always perpendicular to the velocity of the particle, that means that magnetic fields are centripetal forces. They cause charged particles to go in circles. It's very easy to figure out the equation for how big a circle it would be by taking the magnetic force and setting it equal to centripetal force. So QVB sine theta, theta in this case is going to be 90, so sine is 1. So QVB equals centripetal force mv squared over r. We can then solve that for whatever we want. If we solve for radius, we get mv divided by QB. This is called the cyclotron equation. MV, of course, is momentum. And so we can say if we know the momentum of a particle, we know how strong a magnetic field we need in order to get it to go in a particular radius. So that's the cyclotron equation. You could be asked to derive that on the AP2 exam, I think, but it's a very easy one. Magnetic force equals centripetal force. Solve for whatever it is you're looking to solve for. Oh, and one final note, if you have a particle where it's not perpendicular, if the magnetic field is at an angle, then the component that is perpendicular will go in circles, and the component that is parallel will go straight. So charged particles in magnetic fields in that situation will go in spirals. One way will not be affected, the other way will become circular motion. On this same topic, every year I get asked about how a railgun works. So when people hear railgun in these days, in 2020, they often think like this. They think Halo, this man-portable pew-pew. That's not really realistic. What we use railguns for right now is, say, on naval ships. We have some railguns that are really rather impressive, and we can also use them to launch things. NASA can use them to launch things at pretty high speeds. The major advantage of a railgun is that it doesn't require any propellant, meaning it doesn't require like a burning rocket, or it doesn't require gunpowder or something like that. Let's take a look at what a railgun does in a little more detail right here. The idea here is that you have a pair of rails bridged by whatever it is that you're throwing. When you send current through the rails, each piece creates its own magnetic field. You can use the right-hand rule to figure out the direction of each of those. And then you can use the flat-hand rule to figure out the direction of the projectile. Hopefully that would be away from you. This creates a very large Lorentz force as long as you have a huge amount of current, which we can supply with capacitors that have been hooked up to, say, a nuclear power plant aboard a naval destroyer.